So due to from technical problem. So, welcome to the fifth technical session of International Conference on Futuristic Materials. In this session, we will have a plenary talk by Dr. K.K. Reddy, followed by three invited talks by Dr. K.D. Dubey, Dr. S.T. Salamal, Dr. Sachin Kesing. So, to start this session, I would like to invite Professor S.N. Tiwari, sir, the Dean of Faculty of Science and convener of this event, to conduct this session. Professor Tiwari, sir.
Thank you, Dr. Ambrish. This is the today's, I think, last technical session. That is the fifth technical session of this event. We have a plenary lecture in this technical session that will be delivered by Dr. K.K. Reddy. Dr. K.K. Reddy is one of us. He did his MSc in bioinformatics from Pondicherry University. Then he moved to Algappa University for his PhD in bioinformatics. Afterwards, he went to National University of Singapore for doing PDF, where he stayed for a long time. Afterwards, he served as a faculty member at the Albany State University, Albany, Georgia. And presently he is serving as assistant professor of bioinformatics at Hawaii State University, Maryland, USA. I'm very much privileged to invite Dr. K.K. Reddy, who has published very important papers and also around 30 papers of very importance and contributed a lot to the field. With these words, I invite Dr. K.K. Reddy to deliver his plenary lecture on anti-cancer drug delivery using Chitosan functionalized carbon nanotubes through molecular dynamics simulation. Dr. K.K. Reddy, please.
I'll try to.
Dr. Reddy?
Yes, I can hear. Good evening, everyone. Thank you, Professor Tiwari, for a nice introduction. And I thank Dr. Srivastava for inviting me one more time. So today I'm going to present on anti-cancer drug delivery using Chitosan functionalized carbon nanotubes using through molecular dynamic simulations. I'm a core structural bioinformatics faculty, but I did few work, one work I've done in this modified carbon nanotubes. I worked during my one of my last 2 years. I've worked on it, so I'm going to present it on it. So I'm an assistant professor and also the bioinformatics program coordinator here at Bowie State University. So I'm a pretty new faculty, and then we are a new lab. So still we are establishing lab. So I've joined this university during the pandemic. So I think you know that it's a pretty hard to establish a lab right now because we are not allowed for to enter the university. So once again, I just thank organizers for organizing such a wonderful conference on futuristic materials. So we all know that carbon nanotubes are widely used, I mean, for drug delivery system. So there are many nanomaterials that are they used in a drug delivery system, including liposomes and micelles and dendrimers. These all widely used for drug delivery systems, and also carbon nanotubes are also widely used. So since the discovery in 1991, I think they have used quite great number of applications, including electronic circuits and nanocomposites, sensor devices, and then smart textiles, and also drug delivery systems. So today I'm not going to talk about other kind of nanocarriers. So what we have used, I'm going to talk about carbon nanotubes, which is mostly single-walled carbon nanotubes I'm going to talk about. So how we have used this single-walled carbon nanotubes for how efficient loading of these anti-cancer drugs, doxorubicin and paclitaxel, and then how we done controlled release of these drugs. So we all know that pristine carbon nanotubes, which is nothing but without any modified carbon nanotubes. That's what pristine nanotubes are. Highly hydrophobic, we know that, and it's also shows pure solubility and dispersibility. So in our study, we have used single-walled carbon nanotubes. So there are different kinds of carbon nanotubes. There are multi-layered and double-layered carbon nanotubes. In our study, we have used single-walled carbon nanotubes. So why we have used this single-walled nanotubes? Because we can easily modify this single-walled nanotube easily with the biomolecules. So what we have done was we have functionalized this single-walled carbon nanotube with the biomolecule, which is a polysaccharide, which is chitosan. So this chitosan facilitates, the interaction of this. This chitosan which functionalize this carbon nanotube. So there are different kinds of functionalization. There's both covalent and non-covalent modification. But here we have used non-covalent modification. I'll tell you what is the advantages of non-covalent modification in place of covalent. So we know this is a common practice. There are many people, they used covalent modifications, and then there are a few people have done non-covalent modifications also. There are common practices in drug delivery systems. So what is the advantage of this non-covalent type of functionalization? What happens is that allows that is a controlled release of the drugs with mostly the improve the bioavailability, and also increase the specificity and sensitivity, and also reduce the pharmacological toxicity. So we all know chitosan is a polysaccharide biopolymer, which consists of both beta-1,4 linked D-glucosamine, together with some N-acetyl D-glucosamine. So this chitosan can be obtained from the deacetylation of natural chitin. So we all know chitin is a widely available biomolecule, so which is present in the shells of crustaceans and insects and many organisms. It's widely available. And also, so this chitosan, which is modified SWCND, why we have used this chitosan? Means we have used 3:2 ratio. So which is in the totally we have used 30 units of these glucosamine units. So 3:2%. We have used in 3:2% of GCS and NAC. So what is nothing but is that we have done a deacetylation of the these chitin. That is nothing but which is a chitosan. If you see the structure here on the right hand side, just I've shown the how we wrapped this single walled carbon nanotube with the chitosan. So this is we have using MD simulations. We've wrapped that using we've wrapped this chitosan on the SWCND. So chitosan, we all know it is widely used in pharmaceutical applications because of its low toxicity and biodegradability and biocompatibility. So if you see there are wide applications of chitosan. So they've used in tablets, and they've used in beads, and then films, and then in a tablets it is used in matrix coating, and then it is used in microspheres and capsules, and then it's also used as a conjugates and nanoparticles. It's widely used. I mean, chitosan has been widely used in pharmaceutical applications. It is not something new. So because why they've widely used because of its low toxicity. Because if you, especially when you use carbon nanotubes and all, it's a more highly toxic. So it's a low toxicity and biodegradability. That is very important, and also compatibility, biocompatibility. So anything we are taking into anything we are taking as a form of a tablets or something, it should be low toxicity and biodegradability and biocompatibility. That's very important. Then that chitosan has it. So what we have shown here is the co-delivery of DOX, which is a doxorubicin, and paclitaxel, and it's a PTX. So these is widely used drugs for cancer. What we have used is that we have shown how we can load the drugs, co-loading. So there are many papers we have done co-loading, and then they stopped there. But we have shown something different in our study. I'm going to talk about it. So we have shown how we can release these drugs in the cancer environment, in the tumor environment. So doxorubicin is they've used widely for different kinds of breast, including breast cancer and lung carcinoma, and then it is widely used. And paclitaxel is also one of the drug which is also widely used for cancer. So this combination, this DOX and PTX, which has been used in the treatment of metastatic breast cancer. Recently, there are one study I've seen that they've used high density lipoprotein nanoparticles for this co-delivery of the DOX and PTX. So yeah, I've seen there are other studies which they have done co-delivery, but we have used something different approach, that is pH controlled drug releasing. So yeah, it's very easy to load the drugs and see in your experiments that how we can load the drugs, but it's very difficult to show that how the drug releases. So what we have used is pH controlled drug releasing. Why we have used this pH controlled drug releasing? Because the cancer environment, if you see the environment of the tumor environment in the surrounding area, which is highly acidic. So if you see the blood pH, which is normally around 7.4. So, but if you see the cancer environment, the tumor environment, microenvironment, if it is around 5 to 5.5, 5.7, it is very highly acidic. So what we have done is that we use this pH responsive ductility system. So which is one of the has been reported as one of the most important triggers, because the acidic environment of the tumor, which is normally higher than the blood and normal tissues. So for this study, we have used Chitosan modified single wall carbon nanotube. So, and then we have shown that how we can load the two drugs, anti-cancer drugs, both DOX and PTX, on this Chitosan modified single wall carbon nanotube. And then we have shown how we can release these drugs at the target site. That's a cancer target site. So pH sensitive anti-cancer drug carriers can be highly selective to malignant cells. So yeah, we have used one single wall carbon nanotube, which is approximately the diameter around 16.5 angstroms, and the length of the, we have tried multiple angstroms. So of a carbon nanotubes, I mean, in the diameter wise, we have tried different levels, but we found these 16.5 angstroms. I'll tell you why I've used the 16.5 angstroms of diameter of single wall carbon nanotube. And then because we have done one more study, which is the encapsulation study. We want to fit these two drugs, both DOX and PTX. We just want to be tightly packed in the into the halo tube of this carbon nanotube. So that's what we found, that 16.5 angstroms is one of the good way to put it, both these molecules, DOX and paclitaxel, in the halo structure of carbon nanotubes. So we have used Chitosan, which is mostly consisting of 30 units, which is 3:1 ratio, means like which is beta 1,4 linked N-acetyl, means glucosamine, and then N-acetyl glucosamine. We have used in a 3:2 ratio. And then obviously we have used two drugs, DOX and PTX. And then we have used the molecular dynamic simulations and binding free energy calculations to show how the co-loading and releasing of drugs happens. So in our study, we have used, I've developed 4 kinds of systems I've studied. So yeah, I've studied multiple things, but for presentation, I've shown, which is majorly 4 different kinds of systems which I've used in my study, which showing both loading with the pristine, loading with the functionalized, and then protonated, and also the encapsulated. So if you see the functionalized, initially we have done with the pristine, so means we have not modified the carbon nanotube with the Chitosan. Initially, if you see the first one, which is we have used, which is a pristine. So on the second one we have used, which is the functionalized carbon nanotube. And then the third one we have used, which is a protonated. Both Chitosan and then drugs are protonated, and then we have shown how the drug releases. And the fourth one we have done, which is we encapsulated this DOX molecules in the carbon nanotube, and then we have studied encapsulation studies. So initially the first system for the SWCNT, which is nothing but without any modified molecules. So we have loaded 4 DOX molecules and 4 PTX molecules. So here no protonation has been done, no functionalization has been done. And then we have shown that how different it is between pristine and functionalized carbon nanotubes. And then in the functionalized carbon nanotubes, also we have used for, what do you mean by functionalized? It means we have wrapped these Chitosan on the surface of the carbon nanotube through, that's what we can say functionalized. So here, if I say functionalized, means which is a carbon nanotube with the covalently interact Chitosan. So here in the functionalized carbon nanotube, we have also used the 4 DOX molecules and 4 PTX molecules, and there is no protonation has been done. And then for showing this protonation, yeah, we have protonated both drug molecules as well as chitosan. So, and showed that how we can release the drugs. Let's get into the results part. So, we've used all atom MD simulations for all these systems, and then we have done binding free energy calculations in order to show the difference between the binding free energy difference between different systems. Initially, we have done co-loading, and then we have shown that what's the difference between the binding nature of both DOX and PTX, and also their releasing nature and co-loading nature differences between these two. So if you see, initially we have done, first step we have done is the co-loading of anti-cancer drugs on a pristine single-walled carbon nanotube. So if you see here, the first one in the A, which is there is a front view, and then there's a side view, which is this DOX molecules, which has a mucus conjugated benzene rings, which sits perfectly on a carbon nanotube. It forms majorly pi-pi interactions with the carbon nanotube. And then if you see the PTX, which is there are three. They don't have a conjugated benzene rings, but if you see that there is a one benzene ring, majorly it forms pi-pi interactions. I just shown in the C and D. I've shown the distance between the carbon of carbon nanotube and also the heavy atoms of drug molecules, and in order to show how well they loaded onto the single-walled carbon nanotube. So on the right-hand side, I've just shown the radial distribution functions of these selected atoms of a drug molecules. So which is showing the close interaction, close proximity to carbon nanotubes. So it's well colored. We have initially what we did, we placed these drugs far from the carbon nanotube, and then we've done a simulated, and after a few around 50 or nanoseconds, I think around 30 to 50 nanoseconds, it's well loaded onto the carbon nanotubes. We didn't place like this, which is shown on the picture, but we placed the drugs. We have given an environment, and we have simulated it, and then we got a very, very good loading of these anti-cancer drugs on pristine carbon nanotube. So initially we have done, which is in spite of being far from these drugs from the carbon nanotubes at the beginning, when we do these MD simulations indicated that both have a strong affinity towards the pristine CNT. We know that it's a strong affinity. There are other studies for the drugs have strong affinity to CNT. So we found comparison between these two. We found quite different binding nature of these two molecules during simulations, but only one DOX molecules, which always overlaps on the other DOX molecules. But I find other three DOX molecules, which are quite stable throughout the simulations. They form majorly pi-pi stacking. But whereas PTX majorly shows pi-pi and then CH-pi interactions. So this is quite different, but we find stronger binding of a PTX than the DOX. So how we have done functionalization? So how we functionalize these carbon nanotubes with chitosan? Initially, we just place these, if you see in the 0 nanoseconds, we just place the two molecules, which are both chitosan and carbon nanotube, and side by side. And then we found, slowly we found this wrapping this. Until it wrapped completely, I've done simulation, but I found around 50 nanoseconds is almost wrapped. By the time of 100 nanoseconds, it's completely wrapped. This chitosan is wrapped. So I've used this functionalized carbon nanotube for further studies. Initially, I just want to show the differences. That's why I've done for pristine. And then we have functionalized this for chitosan. And then this non-covalent functionalization is very important because it won't affect the electronic network of the tubes, and it won't damage the carbon nanotubes. That's the reason, one of the reason we have used non-covalent functionalization that I've seen other people, they've done covalent functionalization also. So, but with the modifying this with the acidic and amine groups. So what is the thing, why we want to do functionalization? So this functionalization improves the dispersibility and then biocompatibility of this carbon nanotubes, which eventually, I mean, this helps in the transfer of the drugs into the cancer target cells. So the glucose rings of these carbon the chitosan tend to be parallel on the side walls. That's how it's closely wrapped around carbon nanotube. This means with this mostly we found van der Waals interactions. So then we have seen again the difference, the co-loading in the functionalized carbon nanotubes, which is pretty much, I don't see this drug molecules binding to the chitosan, that they majorly they bound with the carbon nanotube. So because wherever you find the spaces, and they perfectly bound to the carbon nanotubes, even though if it is functionalized. To quantitatively discuss the difference between the co-loading of the pristine and functionalized, what we did is that we compared the binding and free energy differences between both pristine and functionalized. When we considered these functionalized SWC as a receptor, we found these still being rather similar exothermic, and there is a significant entropy loss, but we don't find much. It won't. We know that functionalized weakens this binding of the DOX and PTX molecules at some degree, but this functionalization, it will improve the dispersion of the drug delivery system. Then we compared the differences between these two kinds of things. We found a little bit, there is a decrease in the binding energy, free energy, with the functionalized carbon nanotubes, but still this will improve the dispersion of the, I think it's not the drastic changes. So then finally we have done, which is one of the interesting, which is releasing of the drugs. There are many studies for co-loading. So what we have done different is that we know that all the cancer environment is highly acidic. So the pH sensitive release of the drugs is useful with the targeted drug delivery. So what we have done is that we have protonated both chitosan and both the DOX and PTX molecules, because when the drug molecule or chitosan enters into the cancer environment, there is a chance of they're protonates, right? Because it's very acidic in nature. So we compared these by calculating the distance. So then again, we simulated the system and found and see the differences between these pristine, functionalized, and protonated. But if you see how we shown it is shown as a releasing, is that because the difference between the binding free energy, also the distance. So if you see the distance between carbon nanotubes and the drug molecules, in front for you see they're majorly seems like they are releasing. They're very far from the carbon nanotubes, but we did not able to show exactly how it releases either through computational studies. But it shows that we calculated based on the distance and binding free energy. We've shown that it can be released using protonation. So and the one finally we have done, which is want to see whether encapsulation of a DOX also can be done. We have not done extensive study on it. What we have done is that we placed two drug molecules, DOX molecules, in the carbon nanotubes, and we have seen if you see the DOX and DOX2, which is the two drug molecules we placed inside the carbon nanotube, they have a higher binding free energy. We all know that anyway, because when seen inside the carbon nanotubes, there is a more chances of. This is also one of the route we thought that we may explore, but we are trying to do how we can release these drugs. So loading was easy. Loading is easy to do on carbon nanotubes. We want to show that how we want to do this releasing that. Still, we are doing it. So I'm collaborating with my former supervisor. So still we are trying to do this. So this is one of the study, which is interesting study I've done, which is different from my work. So generally I work more a lot of proteins. This is one of the interesting study I've done, and then we find which is very interesting. So to do further, and then we are trying to collaborate with the experimentalists to see that how we can use this system for drug delivery system. Use this system as a drug delivery system. Especially we want to, we are collaborating one scientist from University of North Carolina. He is planning to do these, use this system for his studies. So yeah, thus functionalized, yes, one more minute. So yeah, we have functionalized carbon nanotube, which is plausible for the co-loading. That's what we have seen, that is good for co-loading and releasing of both anti-cancer drug molecules. And then we can use this. We have shown that how in acidic pH, how these drugs are released by protonating the drugs and chitosan. So encapsulation is also one of the way we can do it, and the encapsulation of these may also play a very important role and should be considered in drug delivery systems. We published this in a few part of this work in PCCP. We are trying to do with the encapsulation studies. We are trying to understand the differences between encapsulation and thing. So I acknowledge the BSc students, and then my students, and then my former advisors. So yeah, I'm pretty new to this university, and then it is very, very close to Washington, DC, which is right, it's just around 10 miles from the Washington, DC. And we are located in this building. So yeah, we are a pretty new lab. So I'm establishing my lab, which is, anyway, I'm a bioinformatician majorly. So we are getting a lot of computers and workstations, GPU workstations. Yeah, if you're coming to this area, I know that many people come for conferences. You can visit us. Okay, you can always reach out to us. And once again, I thank Dr. Srivastava and Professor Tiwari for giving this opportunity. Thank you. Any questions?
Thank you, Dr. Reddy. Yes, of course, there is a question in chat box, but I think you have already addressed that question. The question was related to the type of bonding between CNT and chitosan.
Someone is better mute someone, I think. Yeah, okay. So yeah, I think I have answered that question. Yeah, yeah, it's majorly van der Waals interactions. It's anyway, that's what non-covalent interactions. Yeah.
So there is another question from Professor Umesh Yadav, sir. He asked, do you have studied the pH effect?
So yeah, which we are trying to do that. We are trying to do that, but that's what we have done. That's what we have changed anyway. Our pH changes when we do protonation. That's what we have done, is protonated the drug molecules and chitosan molecules, and see that how because when it enters the drug delivery system, when it enters to the tumor microenvironment, obviously there is a chances of protonation. That's why we have protonated a few drug molecules and see that is there anything, this pH effect on this drug releasing. Yeah, we are trying to do with the experimentalists. So they are doing it, how these really how these drugs are released if there is a change in a pH.
Thank you, Dr. Reddy. There is another question from Dr. DP Singh, my colleague. Have you checked your dispersion compatibility by any theory like Hansen? What was the stability in terms of durability of your functionalized CNTs?
No, we have not checked that. I have not checked that. Maybe I'll try it. I'll take your suggestion. I've not tried with that Hansen theory. What was this? There is a question. What was this?
Thank you, Dr. Reddy. So I think we are running out of time, and I wish you a very good morning. And I would like to invite our chair man of this session, Professor Sharat Kumar Mishra, sir, who is head of Department of Biotechnology of our university, to conduct this session. Professor Sharat Kumar Mishra, sir.
Thank you, Dr. Amrish. And we just had a very fantastic lecture by Dr. Konda Reddy, and he talked about the use of the nanotechnology, nanorods in the drug delivery system. So it has been a wonderful lecture. Now we would like to move for the next lecture. That is, the next lecture will be delivered by Dr. K.D. Dubey. He is from the Shiv Nadar University, and he has done his master degree and PhD from this university only. And then after completing his study from this university, he did postdoc from Israel and Switzerland and then IIT. So he will be delivering the next lecture. I invite Dr. K.D. Dubey. Please start his lecture.
Thank you, Professor Sharath. And am I audible to everyone?
Yes,
Yeah,
sir, you
yeah.
are audible.
Yeah, so let me share my screen.
Yes, please.
So is it visible?
Yes, yes, visible.
Yeah. So good evening, everyone. And I'm especially thankful to organizing committee and Dr. Srivastava and Professor S.N. Tiwari for giving me this opportunity. And it's long time I am interacting with my, I will say that my teachers, and it is really nice to present my work in Gorakhpur University. So basically, I started all my study from BSc to MSc and PhD from Gorakhpur University. So today I'm going to give a talk about tweaking chemistry by oriented electric field. So I will start with some type of a story. The thing is that whenever we are talking about any type of the reactions like bond formation, bond dissociations, so we know that all these things are totally a game of the molecular orientation. Like two molecules or two atoms, when they came close to each other, they will interact. And because of these interactions, there will be some reactions, there will be some bond formation, and there will be some dissociation of the bonds. So means that overall, whatever we do in the chemistry, totally our entire motive is just to change the orientation in our desired format so that we can either accelerate the rate of reaction or we can inhibit the rate of reactions. So the thing is that just you can see that this is a very small animation, and we can see that actually these molecules are totally dynamic, and because of this dynamic nature, they may interact with their surroundings, and because of these interactions might be actually they can react and they can form a new compounds. So the thing is that so therefore whenever we think about the chemistry, so overall we try to make the molecules as a dynamic. So because of that one, so what will happen, we have some type of subtle methods, just for example very precise laser to microscope, and also we have some not so subtle methods, just for example stirring the compounds and then heating. So overall in all these process, either we are stirring our compounds or we are heating the compounds. In every cases, what we do, we actually choreograph the dancing, and we try to regulate the dance or dynamics of the molecules. So what happens actually, this is very, you may say that some type of orthodox way, just for example, heating the molecules or stirring the molecules. So these are, you may say that some orthodox way to create the dynamics in the compounds of the molecules. But what happens in some of the groups, there are some, in somewhere in the words, there are some groups, so which have some unusual idea to just regulate this choreography or to regulate that type of motion. And this new idea is actually unusual because this is, you may say that this is a type of unorthodox way. So these groups are one Professor Session. So he was my ex-mentor in Israel. And then Professor Michel Cout. So he is from Australian National University. And Professor Darvis, he is from University of Barcelona. So these were three people, or I will say that currently they are working on some very unorthodox or very unconventional way, where they want to tweak the chemistry just by using some oriented electric field. So what happens actually in their methodology, they just align some electric field along the axis of reaction, and just by applying electric field along the axis of reaction, they found that they can actually accelerate the rate of reaction, or they can inhibit the rate of reactions. Basically, this idea, like recently Professor Chitosan mentioned in one of his autobiography, that he got this idea in 1974. And what happens, actually, he was attending one type of seminar in Washington, and he found that there was one lecturer, or you may say that a speaker. So he was talking about some type of reactions. So that reaction was actually tertiary butyl chloride. So that speaker was mentioning that whenever this tertiary butyl chloride was dissolved in the ether, he found that actually the amount of the product formed, that was very small, means that actually it gave a very small amount. But what happens whenever actually he used this very simple salt, just for example, like lithium perchlorate, he found that actually the amount of this product actually that increased by millions fold, means that the rate of reaction actually increased by millions fold. So actually Chitosan mentioned that in his biography that this was actually a type of very fascinating idea. And then he went to his lab and he started thinking about in this direction. So actually what happens, he modeled some compounds, and by this modeling he compounds, and he found that whenever we are just adding some type of concentration of this simple salts, just for example lithium perchlorate, he found that if I am putting this tertiary butyl somewhere, so he found that there are just 2 to 3 molecules of lithium perchloride, they are surrounding this tertiary butyl. So that's why he thought that if we are increasing the concentration of this simple salts, there are only 2 or 3 molecules can surrounding this tertiary butyl chloride. But why? It's mean that if there are small concentration or if there are large concentration, every cases, since it is surrounded by just 2 or 3 molecules, so the rate of reaction should be constant. But he found that actually it is not the case. Whenever they are increasing the concentration of these simple salts, the reaction rates was increasing by millions. So actually he was little bit puzzled, and then he started thinking, and he calculated the dipole moment of entire complex, and he found that actually these simple salts like this lithium perchlorate, actually it is creating a local electric field, and this local electric field is actually catalyzing the reaction. And that's why whenever they are using ether, the product is very small. But whenever they are using the electric field in forms of this simple salt, actually the rate of reaction increases by million folds. So that actually gave him a very fascinating idea that now there is no need for some type of chemistry wet labs, like people are using a lot of catalysis, the industrial catalysis, and they are using a lot of compounds, and they are trying to catalyze the reaction. But whether it will be very interesting, just assume that we have compounds and we are just taking 2 potential differences and we are aligning the molecules along the axis and just switch on your electric field, and now we can actually regulate the rate of reaction. So he thought that if anyhow we are going to implement this in the science, that is going to give a fascinating results. So in that direction, actually he started working. And what happens later on, he developed some type of theory, and basically he is a biochemist. So he used this method in this porphyrin, or you may say that some type of heme porphyrin, and he applied the electric field along the axis. In this figure, as you can see that this sulfur, iron, and oxygen, this is axis of the reactions. So what happens when he actually applied electric field along the axis and the opposite axis? In both cases, actually, he found that whenever electric field, just for example, if you are treating as a 0 scale, so he found that in one direction, actually it is catalyzing, and in another direction, actually it is inhibiting. And if he is going to change the direction, not in the axis of rotation, but somehow in sideway, he found that this compound, just like you can see that this is one type of alkene. So actually, whenever electric field he was applying along the axis, he was getting the reaction as this oxidation of this alkene. But whenever he was applying the electric field somewhere by side, he found that actually now it is not giving the hydroxylation, but it is giving some type of epoxidation. It's mean overall, he mentioned that now we can see that just by reorienting electric field, now we can change the product formation, we can change the rate of the reaction, even we can also change the regio selectivity and the stereo selectivity. So that's why actually he told that, like in his biodata and in biography, he mentioned that now this is you may say that a very small reagent which can use for the catalysis and just to catalyzing reaction, or if we want to inhibit some reactions, we can apply electric field in different directions. So all these story later on, actually, I found that from starting from 1995 to something around 2010, he published many papers. And actually, he gave this type of logic that what happens when we are applying some electric field. So we know that whenever we are going from a reactant to product, there will be transition state. So whenever we are going applying electric field, this electric fields actually stabilizes the transition states, and that's why the barrier gets lower, and in that case, this reaction actually accelerate. And if you are applying electric field opposite to the transition state, it may destabilize the transition state, and that's why the barrier goes high and it actually inhibits the reaction. So this story, or you may say that this logic was actually accepted by the many scientific community, and they were convinced from that one. But what happens, actually problem created in Sessions group. What happens, actually he used this oriented electric field by this, we may say that this DL-centered reactions. So actually, he published this paper in something around 2009. And in this paper, actually, he mentioned that even this oriented electric field can also accelerate the reaction of DL-centered reactions. So, but problem is that in this reactions, there is no transition state. So this actually created a problem to the Sessions group. And now scientific community was not accepting his logic, because in the previous logics, he mentioned that electric field can stabilize the transition state. And that's why we are getting a low activation energy and reaction is actually accelerating. But in this case, actually, in these reactions, there will be no transition states. Then how actually this reaction is going to be accelerated? So then people, those experimentalists, they started questioning this logic, and they told that now, since you people are theoretician, you can model anything and you can propose anything. So after this 2009 paper, that was a roadblock to the Sessions group, and he struggled a lot, and then he was not able to even publish any paper in oriented electric field. And then actually he motivated in cytochrome P450 and other biochemistry project. But what happens in 2016, there was one Australian group like Michelle Coot, as I mentioned. So she actually motivated by this paper, she was the first time actually she experimentally verified this concept given by the Professor Session. And actually she mentioned that this is a type of proof of principle by experiments. So what she did, she attached the same whatever the compounds with these gold plates and applied electric field like a voltage difference along this way. She found that actually whenever this reaction is going on, there will be some type of, this circuit will be complete and there will be some type of pulse. She found that whenever she was increasing the potential differences, the rate of this pulse was increasing, means that the rate of this product formation was increasing. So it's mean that actually this experiment completely verified whatever the theoretical models or the prediction was given by the Professor Session. So the thing is that after getting this paper, actually by that time, I was working with Professor Session as a postdoc in Israel. So I found that actually he was very excited, and he came to me and he told that, Kshatrish, now don't work on cytochrome P450, just let us start on this electric field, because now our theory, our models has been verified by the experimentalists, and this paper was actually published in the Nature. And this was, you may say, that a groundbreaking research. And even after this work, Sesson got very excited and he started working on the electric field. By nature, actually, I was a biochemist. By that time, I was not interested in working on electric field, so I denied his offer and I told that I am working on P450 and I will work on that one. So what happens after when I joined Srinagar University in 2019? So definitely I had a pressure to create some very good results. So, and I found that actually if I'm going to apply this electric field, definitely this is a less computational cost. So of course I can apply my computational techniques very early. So what happened in that time, actually I rethought about his proposal and I started working on this electric field. And then actually this was my first paper using electric field from Srinagar University. And for this project, actually, I collaborated with Sesson and one of his postdoc, Thies, and my PhD students, actually, Surjit Kalita, he also collaborated here. And then we started working on electric field. So the question is that what actually motivated me to work on this project. So the thing is that, like in the previous slide, whatever the experiments, missile hood they have done, we can see that actually we are applying just one electric field on one molecule, and then we are getting some type of catalyze. So it's mean that that might be a proof of principle, but we cannot use this technique for the industrial scope. The reason is that you can see we are applying one gold plate for one molecule. It means this electric field cannot be used as a scalable, and we cannot use as a parallelization for the industrial level. So that was a big challenge for the session, like how we are going to use this oriented electric field for the industrial level. So what happens when I came here, I discussed him, and then I actually got one idea. In that case, actually what happens, we know that there are ionic liquids like acetonitride, and these are very polar solvent, and they actually produce some local electric field. So what happens, suppose that if we are putting some type of reagents, like some type of compounds, in this solution of this ionic liquids, so definitely this ionic liquids will have some local electric field, and this local electric field may catalyze the reactions. So actually this idea came in my mind, and then I got accepted the offer of Sesson, and then I started working on this project in my lab. So this was the motivation behind this paper, and this paper was published in JACS just 3 to 4 months back. So in near about in May 5 we published. So I'm going to in next few slides, I'm going to discuss the details about this work. So the thing is that actually what happens for my this project, I opted for this Mansutkin reaction. So actually this is a very simple mechanism of reactions, and for my setup, I use this acetonitride as a solvent, okay, and then I put this compounds like methyl iodide, and this you may say that pyridine here, and then I put into the solution. And then what happens? Initially, I calculated what is the barrier of this reaction. So using some hybrid QMM calculation, I calculated the barrier, and I found that actually the barrier of this reaction was something around 19 kilocalorie. And soon, of course, using some DFT calculation, we using the Gaussian, we also calculated the barrier in the gas phase, and we found that actually the barrier in the gas phase was something around 28 kilocalorie. It's mean that this like unorganized this solvent is still actually it is catalyzing, because in gas phase the barrier was something around 28 kilocalorie, but in the solvent, this acetonitride, the barrier was something around 18.9 kilocalorie. So it's mean that this is actually catalyzing the reaction. Now, as I told you that my motive was that just to use this local electric field of acetonitride to catalyze the reactions. So my next target is how to align these ionic crystals just acetonitride. So the alignment of this acetonitride was one challenge. So for that, actually what happened, I did MD simulation in presence of external electric field. So like if we are nowadays, if you are using any type of MD package, either it is Umber, Gromax or Char. So everywhere there are some options to apply the local external electric field on the compounds. So what actually I took this acetonitrile solution and then I performed the MD simulation at different electric field. So we can see that when electric field was very small, almost these ionic liquids were unorganized. And whenever I was increasing the electric field, we can very clearly see that at some electric field like 0.1 volt per angstrom, what we can see that a clear alignment of these ionic liquids. Okay, so we can see that there are very clear alignment. So for further actually just to see that there is some type of organization, I calculated the entropy of this system, and we can see that this is the plot of the entropy as well as electric field. So we can see that whenever I am increasing the electric field, the entropy decreases. It's mean that our solution is actually going in the ordered form. Again, what happens? I calculated the dipole just to quantitatively verify that yes, there are some type of organization of these ionic liquids. So we also calculated the dipole moment of entire things. So we can see that actually dipole moment increases because actually these solvents are getting organized, and at some particular value actually it is gets saturated. So it's mean that now it is not going to, means it is in saturated state. So we calculated all these things, and actually we verified that whenever we are putting some external electric field, this ionic crystal gets aligned, and this alignment actually produces some type of local electric field. So now the next question is that whether this aligned ionic liquids have any effect on the reactivity, because using in the previous MD simulations, I actually solved my first puzzle that how to align this ionic liquids. So it was clear that if we are using external electric field, we will align the ionic liquids. So now actually I just tested that whether this aligned electric field, aligned this ionic liquids, whether it is creating any local electric field or not. So what actually I did, I took this aligned ionic liquids, and again I put my compounds there in, and then I applied this charge plated like positive and negative. I created some model, and then I calculated this QMMN calculation, and then further actually we calculated some type of reaction barrier. So we can see that actually whenever we are using this aligned ionic crystals, so because of this local electric field, we can see that the reaction barrier, which was actually 18.9 without external electric field, now we can see that it is actually 8.3 kilocalorie. It's mean that this local electric field produced by this acetonitrile is actually working as a catalyst, and because of this catalyst, we can see that the rate of reaction has increased many folds. So means that this was a type of a conceptual work, whether we theoretically we verified that if we are using some aligned polar solvent or ionic solvent, so this electric field can be harnessed, can be used as a source for external electric field, which can further catalyze the reactions. Okay, so this was actually the conclusion, and this was the first conceptual article in this direction, and further it has very open, we may say that scope to test it experimentally. So I will finish my lecture very quickly. So already I have 3 minutes. So now I'm grateful for this DBT for my research grant as a Ramalingam Swami Entry Program, and then of course HCL Foundation and Sivnadar Foundation for the resources, and then my research group. So there are 5 PhD students working with me. So Surjit Kalita actually he just joined something around 15 months back, and in this short time actually he published one JAX and SES catalysis, and one EnguChem is already in the review. So might be he, and then Ankita Tripathi. So all these students are get qualified, and they are very actually talented students. So that's all. Thank you. If I'm open for the questions.
Thanks a lot, Dr. Kshatrish Dubey, for delivering such a wonderful lecture on picking chemistry of the materials by oriented electric field. And we are also happy that you are doing good work at Syed Azad University, Greater Noida. Now, for the questions or any interactions, I request the audience to please interact in the chat box because we are already running short of time. Now, I would like to invite the next renowned speaker, Dr. S.T. Salamal, and he is a scientist in MPRI CSAR lab that is located in Bhopal, Madhya
Namaste,
Pradesh.
sir.
And he is basically, he will deliver his talk on the red mud-based X-ray shielding materials as an alternative of toxic lead. So I welcome Dr. S.T. Salamal in this technical session for delivering his lecture. And I welcome on behalf of the organizing committee of this conference. So I would like to request Dr. S.T. Salamal for his lecture. Please unmute him.
को फोन किया था सर्वर गड़बड़।
Yes, okay.
Please, Dr. Salamal.
Okay, now, okay, wait, I will say. So, hope my slide is visible, right? So,
Yes.
Good evening and good morning, wherever you are. So, first of all, before going to my talk, I would like to thank the organizing committee for giving me a chance to present our work in this international conference on futuristic materials. So till now we have had a lot of talk on I think this is the first talk on waste to wealth. So we have seen a lot of talk on organic semiconductors and piezoelectrics and simulation and so on. So here we will talk how to convert the industrial waste into an useful product. So title of my talk is X-ray shielding red mud tiles as an alternative of toxic lead. So what is a radiation? Radiation is a particle or a wave which transport energy from one place to another. So we are living in an era of radiation. For example, we are using for radio waves for the communication till the gamma ray we use for medical treatment. So these when the part of the UV till the gamma ray, they are very high energy. Whenever they interact with our body, they can break the DNA. Once the DNA is broken, it can mutate as a cancer or it can die. So according to International Commission on Radiological Protection, one adult is can be exposed to 20 millisievert per year. So as we know that we are radiation we are using everywhere, for example, medical CT scan and in the energy, the nuclear power plant, they also releases a lot of high energy gamma rays and food sterilization plant, so on. We are using many places. So they are very good if they use safe because they are very dangerous also. So what they do normally, it is very good practice to save, means to work behind the radiation shielding walls. Commonly they use the lead bricks. So they use a thick lead brick and the bricks will be sandwiched between these two concrete walls. Otherwise, they will use very wide concrete walls to build such a radiation shielding structure to 1 to 3 meter wide, depend upon the energy of the radiation. So why they use lead or something? Because whenever a photon interacts with an atom, it can interact through three mechanisms. One is a photoelectric effect. It is depend upon the atomic number Q. And another one is Compton scattering, that is depend upon the electron density. Another one is pair production, that is depend upon the atomic number square. So here we are using red mud, it has a lot of iron. So normally it is a 26 atomic number. The major component will be compound scattering. So I will explain what is compound scattering. Whenever an X-ray interacts with an atom, so it will kick out one electron as well as it will release one low energy X-ray or gamma ray, depend upon its energy. So now this whatever a secondary electron or the photon is still energetic to make further ionization. So it is very mandatory for the next electron to be close by to absorb, so that the attenuation will be much faster. So the density also plays a crucial role in attenuating this radiation. So that's why normally what they use lead or heavyweight concretes they use for radiation shielding application. But we know that there are waste also which has a lot of high Z material. For example, red mud. This is an alumina industry waste. Whenever they produce 1 ton of alumina, they used to produce 1 to 2.5 ton of this waste, red mud. If you go for aluminium, then 1 ton of aluminium when they produce, they will produce 6 ton of red mud. So this is not utilized. Nearly 2.7 billion tons we are having in our world, because it is very highly hazardous because of its extreme alkalinity. And whenever these heavy elements present from this waste leach out, and they damage the soil as well as groundwater also. So because of its hazardous nature, our alumina industry is spending rupees 800 per ton to safeguard, because they have to specially design a dam to store it. It is not utilized because only 2 to 3% has been utilized. The rest all are stored in the disposal plant. We are producing a third largest, and it has a lot of iron, aluminium, SiO2, and other heavy elements which is suitable for radiation shielding application. For example, when such multi-elemental systems are good, for example, whenever they reach their K or L edge, they absorb more. So that multi-elemental system will increase its absorption. So what we did first, know that it is a natural material and it's a mined material. So people will have a doubt that whether it is good for using, because it can have radioactive nucleus because it's taken from underneath. So first we did this radioactive nuclide test, whether it has any radioactive nuclides or not, like which has a uranium, radium, thorium, potassium, which has a very long life. So we tested it. They are used, can be used because they are well below the safer value. And then we went to for this their thermochemical studies, because we planned to do through the ceramic route. So it was decomposing. The weight loss was nearly 10% was there. So initially we found to decompose at 217 degrees Celsius. The aluminum hydroxide, which was present in the red mud, was found to decompose, and it will release water as well as alumina, which is amorphous. So you can see here the XRD pattern of that. So when we go to 217 degrees Celsius, you can see there is no peak of this aluminum hydroxide. This pink color shows the standard diffraction pattern of aluminum hydroxide, and if we couldn't see it any peak in the position, it shows that there is no aluminum hydroxide decomposes. Same with also FeOH also. It is decomposing around 417 degrees Celsius, and it releases water vapor. And around 600 degrees Celsius, this calcium carbonate present in the red mud, it decomposes, and it also releases carbon dioxide, as well as it will have calcium oxide, it will be converted. So then after these thermal studies, we made the tiles through a ceramic route. So as I told already, we are using, this is atomic number is very important role, plays a good role in the radiation shielding. So we added certain weight percentage of barite, barium sulfate with that. Then we ball milled it. And then we have used here various binder like sodium hexametaphosphate, kaolin, and other dextrin and so on, which is commonly used. And then either we dissolve the binder in water, depend upon the binder property. Then we made a tiles, and then we apply 300 kg per centimeter square pressure to make the tiles. Then we fire the tiles between 900 to 1150 degrees Celsius, and we got such a tile. So why we fix that temperature at below 1150? For example, when we go above 1200 degrees Celsius, this barium sulfate which we added, it decomposes and form barium oxide and sulfur dioxide, which is not good for the environment. That's why we fix the temperature up below 1150. and it is sufficient for to have enough strength also. You can see here that at 900 degrees Celsius, we don't see any decomposition of barium sulfate, because you can see this red and blue color. This is before and after firing. So barium sulfate peaks are well matching. So it shows that barium sulfate is not decomposed. So this is when you make tiles, there are two things are very important for the strength and attenuation. For the strength, there is a impact strength and flexural strength. These two are important parameters to use in a structural application. So we did as per the standard by dropping the balls. So we have calculated the impact strength. So we get the impact strength of 22.5 and 21 for SHMB and kaolin. So normally the standard value we must have is 18 joule per meter, but we are getting sufficient. And the another strength is flexural strength that we did by 3-point loading techniques. And then we got this for SHMB is 18 Newton per mm square, and kaolin clay we got 22 mm per meter square. The standard value what we need is 20 Newton per mm square, so that you will be able to transport those tiles. So we found optimum sintering temperature we can have up to 900 degrees Celsius and 10 weight percent binder, and kaolin clay found us the best binder for that application. And then you know why these people are not using such a industrial waste for any building application, and why it's put in the side. One thing is it's the leaching of heavy metals. For example, you can see here before sintering the tiles, this lead and chromium, they are leaching a lot, which is much above the permissible limit. But when we sintered at 900 degrees Celsius or 1100 degrees Celsius, you can see the lead, cadmium, their leaching has been arrested, as well as arsenic. But chromium is little bit leaching, 0.83 ppm. But in normal water, chromium was found to leach around 1.84. But it is still below the permissible limit what we can have in industrial water, that is 2 ppm. So it can be used for the building application. So then we did this X-ray attenuation studies of those tiles. So normally in our hospitals like CT scan, X-ray diagnosis, they use maximum 100, 125 kVp X-ray. But we did the study from 75 to 150 kVp, and we have calculated half value layer. It means that how much thickness we require to reduce the incoming X-rays by half. 10th value layer means by 90% to attenuate. So we did for our tiles. You can see this, for example, red mud with SHMB and barium sulfate. We are getting the half value layer is 1.46. So normally in the CT scanner room or the normal X-ray diagnosis, they use 2 mm thick lead to shield those X-rays. So if we calculate our tile, 2 mm thick tile lead, if you want to replace, we need nearly 11 mm thick of our tile. So, but when we do for gamma rays, these tiles are not good for shielding gamma rays, because we check it attenuation, it was very poor, and then we investigate the tile interior morphology. You can see there are a lot of pores in it. When we calculate this porosity using water absorption technique, Archimedes principle, then we can see the porosity is nearly 30%, which is not good for such a way shielding gamma energies. If we can use it, but we need a very wide wall again, and it will consume a lot of space. So, but this pores, from where it comes, this is coming because during the sintering, I told this calcium carbonate, aluminum hydroxide, and ferrous hydroxide, they are decomposing, and they release vapor, and it will be trapped, and it can also form pores in it. So very recently, what we did, we closed this pores through hot compaction technique. So at various temperature, we press those samples, and we even with the pure, but without adding any barium, we could have get nearly 4.2 gram per cc. But at least, but those pellets are not good. But at 1100, we could get sufficient pellets with sufficient strength, which has a density of 3.5 gram per cc. So when we add little bit of high set materials like bismuth or barium, we could have get the density up to 5 gram per cc. And the other thing is the strength. Here we need, if you want to build a structure, the compressive strength is very important. For example, the lead, I told already, they use both the side, they will use a concrete wall to hold it, because it is structurally very, very weak. But the normal bricks, what we use is its compression is 20 MPa. So whatever the pellets that we made, that pure red mud is having 35 MBA, and with bismuth we are giving 295 MBA, which is more than sufficient for directly building those radiation shielding structures. So we did those gamma ray attenuation at variable energy cyclotron center at Calcutta. So we placed this cobalt 60 source and our sample red mud, and then we use a barium fluoride detector. So we vary the thickness of our sample. You can see here when you are increasing the thickness, the attenuation is also increases, coming down from 1.17 as well as 1.3. So from that, we find out the half value layer by plotting the intensity versus the thickness. You can see at nearly 40 mm thick of this red mud sample gives the attenuation of half, means it suppress half of the beam, means attenuate half of the beam. So we have calculated this half value layer for our sample. So you can see these are the hot plus sample with the high density. So red mud with the bismuth. So 20.78 mm thick is reducing the intensity by half. For example, whenever they use cobalt 60 source, normally they use 180 mm thick lead to build those radiation shielding wall. So if you calculate that, so our sample is needed nearly 300 mm. So it is it means it shows more than half of the attenuation of the lead, and it is cheaper also. So
Dr. Salamal,
this
excuse
technology,
me. Sorry.
I
Sorry
have
to.
just 2 slides only. Finish.
Yeah, sir. Please conclude. Okay.
I'm going to
Thank you.
finish. Yeah. So
Yeah.
our technology has been accredited by Atomic Energy Regulatory Board because it's health related. So they have to be accredited. So we have given this technology to one of the leading tile manufacturer, this is Prism Johnson Limited. And also we made 2,500 square feet tiles, and we use it in one of the hospital in Saidif Healthcare in Ahmednagar, Maharashtra also. So conclusion, so we have made the tiles with sufficient mechanical strength. So 2 mm is 10.5 mm is sufficient to show the attenuation of 2 mm lead, and 300 mm thick red mud bismuth block is sufficient to shield to replace 180 mm lead for shielding cobalt 60. It will vary with respect to the energy, and it can be a better replacement of toxic lead as well as the heavyweight concrete, and it is cheaper because we are using red mud as one of the raw material industrial waste, zero cost, and it will suppress the accumulation of red mud, and it will also reduce primary mining and other environmental issues as well. So, and it is also highly stable. So I would like to thank all of my students as well as my collaborators from VECC and my institute head and director. So I would like to thank you for your attention.
Thank you,
If there are any
Dr.
questions, then
Steve.
I'm happy to answer.
Yeah. Actually, we are running short of time. There is paucity of time. So I would like to request the people who are interested to interact with Dr. Salabel in chat box. And we are very much thankful for your kind presentation, Dr. Salamal. And very good work you are doing, and that's eco-friendly work what we are trying to emphasize on. And let you know how toxic it is in the environment or in the body. And the alternative of the lead is definitely going to make our life easy. So thank you so much on behalf of the organizing committee, and thanks a lot for giving such a beautiful lecture on this topic. So thanks a lot. Now, the last speaker of this session, we have with us Dr. Sachin Kumar Singh. And Dr. Sachin is our colleague here in the Gorakhpur University. And he did his PhD from Banaras Hindu University. And he did PDF from Germany. He is basically working on the liquid crystals biopolymers interactions, and he has been doing very good work here in our university, establishing a very good laboratory also. He's a very sincere worker, and he's serious worker, one of the very serious worker in his field in our country. So he will be giving his talk on the chemistry of aeroyl hydrogen based liquid crystalline materials. So I request Dr. Sachin to kindly start his speech.
Thank you very much, sir. Am I audible?
Yeah, you're audible. Please go ahead.
I'm sharing my screen now. Initially, I would like to thank to the organizing team and organizers, especially Professor S.N. Tiwari, sir, Dean, Faculty of Science, DD Gorakhpur University, for providing me this very good opportunity to present my work here in this webinar. In this presentation, I will discuss about the chemistry of aryl hydrazone-based liquid crystal materials. And in this presentation, 4 sections are there. First section is the fundamentals of liquid crystal. It is very basic concept. I will discuss about the liquid crystal materials so that I may connect to the scientific community who are not working in this field about that liquid crystal. Further, second section is the chemistry of liquid crystal materials. And third section is all about the aryl hydrazone-based liquid crystals. My research group and I am working in this field, aryl hydrazone-based liquid crystal, for past 6 years. So I have a very good experience and the design and synthetic protocols of aryl hydrazone-based liquid crystals. Many publications are there, patents are there in this field. Therefore, I would like to share my experiences with this course. And it is only part of my research work, means some glimpse of my research work I would like to discuss, and then the future prospects. So total 15 slides are there, and I will take only 18 minutes to discuss all those things. When we are listening about the chemistry of aryl hydrazone-based liquid crystal or chemistry of liquid crystal materials, then one question we should come into our mind that what are liquid crystals? And liquid crystal, actually it is not a very uncommon term. It is very common term now, and we all know about that LCD screens, liquid crystal display screens. And for common people, it is connected to the LCD screens, but for the scientific community, these materials are known for very beautiful optical textural patterns, many different mesophasic behaviors, double melting behavior, that is bi-melting behavior. These materials are also known for phase modulation, means switching of phases from one phase to another phase, and these are stimulus responsive. Therefore, very wide applicability is there for these type of materials. Therefore, these materials actually having a very good property, that is very specific physical properties are also there, and therefore it is quite interesting to the scientific community to explore the physical property, to see the chemistry, and to see that its application in various fields. Now, this next question is that why liquid crystal phases are formed. Actually, very intense or core physics is involved for that formation of liquid crystal mesophasic behavior. But for general or common term, these are intermolecular forces actually. And for the common people, or in a general way, we can say that when the intermolecular forces are strong enough to cause the molecule to line up in a particular direction, then there is orientational order, there is crystallinity. But these are not strong enough to hold them firmly in one place, then there is viscosity and fluidity. And therefore, there is a formation of new phase that is intermediate in between liquid and crystal and called as liquid crystalline phases. And this is the monophase, means this is not a hybrid material. This is actually intermediate phase between crystal and liquid. So in generally we can define it, but yes, there is a various definitions are there, and various theories are there. But I'm just defining according to that. Many communities, many scientists of different fields are involved here. Therefore, I'm commonly defining it according to the intermolecular forces. Now, question is that what is the chemistry of liquid crystal? What we are doing, we as a chemist are doing here in this field, liquid crystal field. Actually, we are the people who are providing the materials to the physicists and material scientists according to their need. They direct us to what type of liquid materials they are needing, means having very specific physical properties for the device fabrication. And then we design and synthesize, or there is molecular engineering is there to synthesize these materials. And you can see most of the liquid crystal materials are actually giant molecular structures. These are macromolecular systems, and supramolecular assembly is also involved here, and therefore it is actually core chemistry. This is convergent and divergent synthetic protocols involved here, and also purity is also very important in the liquid crystal materials. So if we see the synthetic prospects of the chemistry, that is liquid crystal materials, so it is a very hardcore chemistry is there and methodology is involved. And after designing and synthesize the materials, we provide these materials to the physicists and material scientists for further studies so that they may go for the device fabrication. Even biologists are also involved to serve the mankind. So in general way, we can say that there is a structure function relationship studies at liquid crystal which we are doing. It is very common term, that is structure function relationship studies of liquid crystal. But the structure function relationship studies of liquid crystal is outstanding challenges, because there is no hard and fast rule. If we pick up or we choose a core, then it is not very easy to convert these type of materials into having inherited particle properties of liquid crystal. First thing is that. Second is that there is a wide possibility, a very high possibility is that these materials may convert into crystal and liquid state. Therefore, that our international community, International Liquid Crystal Society, ILCS, encourages and values the contributors of researchers who are working on the structure function relationship studies, who are observing new major physics behavior, who are designing the molecule having different structural features and giving a particular major physics behavior for the device fabrication. So we can say it is outstanding challenge, and to get a particular major phase on a particular core with a specific physical property according to the need of the scientific community and the devices. Now, you can see as all the advanced field of the science is now totally multidisciplinary, it is the multidisciplinary involving chemistry, that is synthesis, characterization, and study of properties, and physics, which is that study of properties is actually hybrid to that of the chemistry and physics, and then molecular engineers, biologists are involved for the device fabrication. So it is a multidisciplinary approach, and this is our part, that is the chemistry to pick a particular core and further to go for the liquid crystal phases and then analyze it and provide it to the scientific community to serve the human or mankind. Here I am discussing about the chemistry of aryl hydrazone based liquid crystals. This is the core. This core is actually quite common for graduate, even in graduate and postgraduate classes. They design and synthesize this type of core, aryl hydrazone based core. But when we think about that liquid crystal on aryl hydrazone core, then we are actually getting crystallinity in many times, because there is a strong intermolecular interaction, intermolecular hydrogen bonding is there. Therefore, molecules, most of the cases, they form up, they align up in a particular direction. And this is the challenge which we are actually, we are actually working to design materials on this core. So intermolecular hydrogen bonding is there. Also, there is a possibility of keto-enol tautomerism. Means with small changes in the pH, there is a possibility of keto to enol tautomerism is there. We are showing only DFT optimized structures, but we have done many studies to explain it, to go for that why keto-enol tautomerism is there, and what are the parameters, and what is the external environment by which we can convert this keto and enol tautomers of these type of molecules on aryl hydrazone core. Also, there is very wide possibility of getting rod-like molecule, disc-like molecule, hemi-disc-like molecule, and columnar molecule. So many structural features are very good. That is intermolecular hydrogen bonding, keto-enol tautomerism, and possibility of molecular engineering, and wide possibility of its to get the various new major phases. The good thing is with this type of core is that there is also possibility of coordination to the metal ion. It may chelate to the metal ion, and further you may go for the metal containing liquid crystal. There is also possibility of adsorption of of these type of ligand, liquid crystal ligand, to the nanoparticles also. So there is a, you can see it may stack together for the supramolecular assembly. I'm just showing that DFT, but there is single crystalline studies are also there, extra diffraction studies are also there. I will discuss in the next slides. So you can see that it is a core that is having very wide possibility of stimulus responsiveness to get different mesophasic behavior, as well as to modulate its structural features to get different liquid crystal according to our need, and that wide possibility of their chemistry. Now, this is the core. Here I will discuss about only 3 publications on this core. Only total 16 publications were there on this core, which we are getting very interesting results. You can see aryl hydrogen core is there here, and we have added ester bond in this core, and this is the polycatenary system. Polycatenary means, as you can see, that it is insect-like structure, polycatenary. Many catenaries are there, and then you can see from carbon chain length 6, 8, 10, 12, 14, and 16 with alkoxy chain variations. Then there is from carbon chain length 8 to 10, you are getting columnar rectangular mesophages, and with variation in the chain length, you are getting columnar hexagonal mesophages. And it is up to room temperature to 100 degrees Celsius, these mesophages are actually stable. So that is the beauty of this type of core, that these are crystalline in nature when there is no linking group is there, and there is no variation in the alkoxy chain length, but there is phase modulation or switching of phase from one carbon chain length to another carbon chain length. Even you are getting room temperature liquid crystal, which is of the discotic and columnar liquid crystal materials. And it is verified by polarizing optical microscopic studies, DSC studies. You can see that it is room temperature, X-ray diffraction studies. We have also done that theoretical calculations to get that its stacking parameters for rectangular as well as hexagonal mesophages behavior. So switching of phases we have observed, and we have also analyzed it with a different technique. Even same time analysis also there, but to remove the complexity of the slide, I am just showing that result so that I may just convey my message to the scientific community about that beauty of this core. Now, see, this is the diamimetic system. Means we are actually trying to design and synthesize the elastomer, and to get the polymeric materials, and therefore this is the monomer of that elastomer. And you can see that why polyimidic bonded we have added, so that the intense intramolecular interactions can be observed, and then to see that to apply these type of materials for the cilia fabrication and all those things. And you can see that again we are getting columnar rectangular mesophages with different stacking parameters, and it is well verified. It is concurrent reading are there with X-ray diffraction, SEM, POEM analysis, and all those analysis parameters are also there. This is the cover page article of JML. Again, that is the interesting result which are getting with polyimidic bond and ester bond to get the elasticity into these type of materials in the monomeric system. I am just showing, I am not showing the polymeric system into these type of materials. When diamide bond is there, we got actually crystallinity. It is totally crystal materials having columnar rectangular phases at very high temperature. Now see, with a small variation of R here, we are getting room temperature liquid crystal stability up to 180 degrees Celsius. This part is actually under process of patent. That is, we are getting room temperature liquid crystal columnar mesophages up to 180 degrees Celsius into these type of core. We are getting columnar oblique phases, and they are getting different crystalline phases, and this columnar oblique room temperature liquid crystal phases we are observed. And to see whether intermolecular hydrogen bonding is involved in mesophages also, we did X-ray diffraction as well as temperature dependent Raman analysis. Even SCRS, TERS analysis were also done to see that whether, and you can see that up to this temperature range, up to 210 degrees that Celsius, these intermolecular hydrogen bonding is still stable. That is quite interesting, because at higher temperature, most of the cases that bond break. That therefore we published some part in a part as a part of publication, and a few part is also under the process of patent. And further, this is the columnar oblique phases and columnar rectangular phases we have observed. So I'm showing only results of three research papers on these pages. So a number of hydrogen-based liquid materials were designed and synthesized our research group, and so this is the in a summarized way. I just want to say that there is immense possibility in designing development of novel liquid crystals having interesting molecular features and properties. So there is immense possibilities of getting that devices also, because these are room temperature liquid crystals. Even we are in lateral studies, we are working on liquid crystal based sensors, and this is DST funded project in liquid crystal aqueous interface and liquid crystal solid interface. And we are also working on the biosurfactant to use the bacterial samples, Pseudomonas aeruginosa sample, to get that sensing chips and to devise and fabricate the sensing chips to detect the bacteria in water, natural water resources. Even in lateral studies, we are using that SERS, surface enhanced Raman spectroscopic technique here to align the liquid crystal materials, and then it stimulates responsiveness towards a particular light to what we want to actually detect. And this is our plan to merge two techniques together, that is Raman laser technique, micro Raman technique, as well as the polarized microscopic technique together in the same platform, so that we may analyze the liquid crystal phases as well as modulation of their phases and interaction at the same time to get that result, means optical as well as its spectroscopic result at the same time. That simultaneous result with a simple with a single device. So this is my message. And further, here I would like to acknowledge my that institute where I get training and I get scholarship. That is BHU, Abbas Center of Photonics, ENA Germany, IT Guwahati, and SENS. I'm indebted to my parent institute, DDU Gorakhpur University, to provide me laboratories and infrastructure facilities to carry out my research work. I would also like to acknowledge my research student Madiha Rasid, who were working very hard in liquid crystal sensing studies. I would like to, I'm thankful to research funding, DFG. I was DFG fellow, German Research Foundation fellow. They are providing seed money everywhere to me to carry out my research work. Two major research projects are here in my lab, EST, Inspire Faculty Program, as well as DBT. And without the help of these funding agencies, there is a possibility of research is not possible. Therefore, I am also in debt to these research funding too. And thank you very much for your kind attention. Thank you, sir.
Thank you so much, Dr. Sachin, for giving such a beautiful piece of the lecture, that is chemistry on royal hydrogen-based liquid crystalline materials. And definitely you have done a very good work on this topic, and we will definitely get some good materials for the application. Now we are at the end of today's lectures, and that is the technical session 5. We are almost done through, and I would like to thank finally the speakers who kindly took out their valuable times, and they spoke in this conference. I thank to Dr. KK Reddy from BSU, United States of America, for delivering a plenary lecture on anti-cancer drug delivery using Chitosan functionalized carbon nanotubes through molecular dynamic simulations. So he delivered a very good lecture today. The first plenary talk was by him. Now the second talk was by Dr. K.D. Dubey. He is in Shivnadar University, Greater Noida, and he talked about the trickling chemistry of the materials by oriented electric field. And today's third talk was by S.T. Salamal, and he talked on the alternatives of the toxic lead. So he is developing some other materials which can be used in as alternative for the lead, because lead is very toxic. So the last and final lecture just be concluded by our colleague, Dr. Sachin Kumar Singh, who is in the chemistry department in Deendayal Upadhyay Gorakhpur University, and he spoke on the royal hydrogen-based liquid crystalline materials. So I thank all the speakers for giving their valuable time, and I also thank to the participants who constantly they were connected and they were uh, present in all the lectures. I could see Dr. Singh. He is continuously, very sincerely, he's listening all the lectures. So I thank to all the participants, all the audience which took part in this technical session. And finally I would like to thank the organizer, I especially to Dean Faculty of Science, Professor Sugrinath Tiwari, who kindly assigned me the task of to chair this session. So I am really thankful for giving me this wonderful opportunity to chair this session. And I'm also thankful to Dr. Ambrish, who is acting as a moderator and taking care of this. So I'm thankful to the all organizers finally, and also thankful to all the learned speakers of this technical session and the participants. So thank you so much. And now I think we are through with this technical session and today's all the lectures. So thank you so much.
Thank you, sir, for sharing this session. And I also thank all the speakers present in this particular session. And I feel privileged to have Professor N.B. Singh, sir, from University of Maryland, Baltimore County, that he is present in this session. Now I would like to invite our Dean, Professor Esan Tiwari, sir, to formally close this session.
Thank you, Dr. Ambrish. Very good evening to all of you connected with this event. Today was a very packed session. We were having 14 invited lectures, 4 plenary lectures, and 2 special lectures. And since 11 a.m., this day was being actively participated by the experts, speakers, and other people from academics. I'm seeing Professor N.B. Singh, who joined this session now. A very good evening to you, sir. You just started this international conference with such a zeal at midnight that it is being continuously attended and participated. And I am proud of telling you that all the speakers who gave their consent are present and they are participating. And people from our university, Professor Ravishankar Singh, Professor Rakesh Kumar Tiwari, and one professor from Lucknow University, Professor Neeraj Mishra, Professor Dinesh Yadav, and Dr. Shamshad Ahmad Khan from St. Andrews College. He is a very good material scientist. And Professor V.K. Pandey from Madan Mohan Malvi University of Technology. He is now head of the Department of Physics and Material Science. And Professor Sharad Kumar Mishra, who was just chairing this session, and Professor Shantanu Rastogi, present head of the Department of Physics, all contributed a lot to run the sessions today. So I'm grateful to all the chairmen and co-chairmen who supported this session, and above all the invited speakers and plenary speakers who graced this international conference by their glorious presence and illuminating talks. With these words, I take the opportunity to thank you all again and again. Now the session ends, it comes to its closure. With these words, I hope tomorrow at 11 a.m. again we will meet finally celebrate the third day of this international conference. With these words, thank you all. Thank you all for your attention.